Good afternoon and welcome to this webinar provided by bobwillis.co.uk. We're also welcoming delegates from the SMTA. My name is Bob Willis and I'll be presenting today's webinar. I'd first like to explain the control panel that you have on your screen at this moment in time. Now, the control panel allows you to do a few things during the webinar. First of all, you can open and close the control panel by clicking on the orange button. This prevents it obscuring your view of the slides during the presentation. You can make the image on your screen or on your projection facility in your conference room go full screen by clicking on the button here indicated by the red arrow. At any time during the webinar, you can type a question directly into the control panel. And sometimes it's best to type a question while you think about it, or if you're in a conference room with a couple of colleagues, then they can type a question in at appropriate time during the presentation. We'll answer the questions at the end of the webinar this afternoon. Now, if you have any technical problems, please use one of the telephone numbers provided on your registration and reminder emails. You'll also need your webinar ID number and access code, which was included on your email during registration. It's not possible for the presenter to assist you during a live presentation. Please remember also that the internet is generally still under pressure, and you may find the local speed issue in your area, your country, or possibly even in your own facility if everybody else is watching YouTube. At the end of the presentation, we have a couple of survey questions. Just take a couple of moments to complete. It gives us good feedback on the webinar, its content, and also on topics you would like to hear me present in the future. We'll be sending a copy of the slides shortly after the end of the webinar this afternoon. A little bit about me. I've been involved in electronic manufacturing all of my working life as a mechanical engineer. I've been involved in training consultancy worldwide over the last 40 years, and I've worked with large and small organizations worldwide providing training courses, failure analysis, and also producing training material for those organizations. So that's just a little bit about me, my activity, and my practical activity in electronic manufacture. In addition, you may find some useful videos online. I've produced countless videos on different types of process defects and book reviews and a variety of other things that you might again find useful. Again, that's all available on my YouTube channel. And you can take the link or just do a search on YouTube for my process video defect videos. So, into the topic of today. We're going to be talking about moisture sensitivity of components and also moisture sensitivity of printed circuit boards. But first of all, just a little bit of terminology. MSD stands for Moisture Sensitive Device or Devices. So that's any component that might suffer from an effect if there is a high level of moisture within the package or the part during an assembly and soldering operation. And the sensitivity level is not given to PCBs, but it is given to components. And that's something that is defined by the component producer. And obviously every component producer wants to set a standard which you don't have to worry about, i.e. it doesn't matter how long the parts are outside of their protective packaging. However, if they set the specification too high or too low, that may have an impact on designers using the part in manufacture. So they need to be sensible, they need to do their own tests and qualify their parts to a certain level. So surface mount components is really the first area we started to see problems of moisture in parts during the reflow soldering process or during the rework process. We've seen it with printed circuit boards for many years, and we normally relate that to delamination of the printed circuit board. And I'll explain about both of these issues and how they occur, and also demonstrate on what to look for. Now, if we look at through-hole parts, it is possible that during rework and repair, and also if you're using some parts with intrusive reflow, this is pin and paste reflow, then again, moisture sensitivity may not be documented from the supplier, but it may be something you need to consider as well. So if we just look at surface mount components, as you know, there are a myriad of different parts, and generally speaking, we're talking about plastic packages, but also packages that are partly plastic, partly fiberglass in their construction, like area array and BGA packages can suffer from this particular problem. And it's something that has been around for many years, and I can remember distinctly the very first issue that I saw was way back when I was working with GEC, and that was sort of in my 20s. So again, it's not something that is only just appeared, it's something that has been around for quite some time with components. So what fundamentally happens when you have a package, it's exposed to a higher humidity or moisture from some other source. Moisture can accumulate within the package, and you'll see a very small change if you were to weigh the part, but the moisture being present in certain areas, particularly if there is any voids within the plastic package, can cause the package to expand as the package is heated. So what is actually happening is the plastic is being moved away from perhaps the lead frame, from the die, from the bond wires that I show in this particular diagram. And when that occurs, when this movement occurs, you get a kind of a blooming effect or a bulging effect on packages. And you can see I've represented it here with a red stripy line. So moisture tends to accumulate, the package tends to expand, and you may hear it go pop. And this is why we hear the term popcorn and popcorning effect. And you don't normally hear this associated with a reflow soldering process. It's when we're talking about rework and repair. When you're concentrating very closely at a component during rework, it's then that sometimes you hear the little pop take place. And if you're concentrating really, really carefully, sometimes it can actually make you jump. It's not loud, but you can hear it. So in this situation, what is actually happening is we can get discontinuity, so a loss of function, because this moisture is causing parts of the package to separate. So visually from the outside, you would see a crack. And the crack would either be at the top of the package or the bottom of the package. It may be at the side. So I've indicated here 3 examples, both top, bottom, and side. It is generally unusual to see it on the bottom. I've tended to see more cracking on the tops of packages. But then again, if you had a problem which didn't actually cause a fault at that time, if it was on the bottom, you would never know. So sometimes what my perception might be incorrect because we're not actually looking at the package at the bottom all the time. But if you do failure analysis, then you would be able to detect where the actual cracking was on the package. So that's an example. And then what actually happens, which causes a problem with functionality, is we can disrupt the bond between the bond wires, and you can see that top right that I show where the little bond wire has been pulled away, and it might be intermittent, it might be completely failed. In addition, you might see, depending on the way in which the die has been bonded to the lead frame within the component, you might see cracking underneath that. Again, illustrated by the bottom right photograph, where you can see the die separating from the lead frame. So this is what actually happens during this popcorning phenomena. You may not hear a pop, you may not see a crack, but you might see some discontinuity if you don't look after the packages prior to the assembly and soldering operation. And this is just a close-up view of 2 of the cracks that I showed you previously, and a little explanation on what cracking can occur. So that's what would happen. That's what you might see if you investigated. And this is a first video. And what this does is actually show you popping happening in reflow in vapor phase. And this is me running a test board in vapor phase with a lead-free solder. So we're soldering at a peak temperature of 240 degrees Celsius, and you'll notice the component is moving. And this is a repeating video, so the video is going round and round and round. So the jump is when energy is escaping from the package and actually moving the package. Because it's in a vapor, it's a little bit more difficult to see, but there actually is a pop of water vapor coming out of the package, which is propelling this device across the printed circuit board. So that's just a trivial example, but a real world example of this happening in a production process. Now, I was asked to make a couple of videos for a company a couple of years back, and this is useful again just to show you what's actually happening. So if we look at the first video on the top, and then watch for the arrow, and then watch for the puff of smoke. So what you saw there is just a little puff of smoke directly where the arrow was positioned. I'm going to run that again just so you see it. Arrow, and then look for a little puff of smoke, as you see there. And what you would have heard if you were to listen to that is a little pop taking place. Now, the bottom example I show you here again is a package, and you'll actually see the package distorting. So what's actually happening here is expanding because the moisture inside is allowing it to expand. So depending on the degree of that, what the impact might be open circuits on a package, it might just be short circuits depending on how the package flexes on the surface of the board where the solder paste is reflowing, or again, it might not have any effect, but it's certainly something to be avoided. So those are just two good examples of this type of phenomena taking place. So again, just to show you optically what you might see, these are two failure sites on BGA area array packages. So when you've got a plastic package with a fiberglass base on it, you might see the cracking between the plastic and the fiberglass, and it's right at the corner there. I've indicated on the left-hand side, and this is literally at the solder resist to epoxy seal. And on the right-hand side, this is actually in the plastic of the package, and you can see this little line across the surface, and that's what you might see on an area array package if this phenomena were to occur. So I mentioned earlier that if you get a reflow soldering situation where you're soldering an area array package, the package might warp, and I've demonstrated that to you. But if you're soldering the package and this occurs, you can actually also get solder shorts. Now, this is a video I made for a friend of mine to demonstrate this phenomena. And what you're looking at here is reflow of BGA on a piece of glass. So the glass, you're looking through the glass while we're videoing, and as reflow takes place on the solder spheres, the package is warping and distorting, and it's squashing the balls. So consequently, you end up with a couple of shorts on the top center area, just literally from the solder paste and the volume of the solder ball taking place. And we can see this, and we can measure the degree of change if we have an X-ray system which allows direct measurement of spheres. So this is an old photograph, quite old, probably around 10 or 12 years old, but it's an experiment that I was doing, and I wanted to demonstrate how you could measure and quantify degree of warp of a package based on looking at ball size. So what you're looking at here is all the balls, and they're measured, and we could argue that perhaps they may be 10 microns out or 12 microns out, but it's the relative variation that you can see. Again, it comes down to the calibration of the X-ray system that you're using and its capability to do these measurements. But what you're seeing is a variation in the size of the spheres. And again, if you take this into a spreadsheet, you'll be able to compare the numbers. Now you can see obviously 3 areas where you've got balls and chip component on the opposite side of the board, which looks like a massive short. It's not actually a massive short, but you can see the variation in ball size if you compare all the numbers. So again, if your system, your X-ray system, has that capability, very, very useful tool to help understand the problem. Here, again, we're showing the phenomena of failure. And in this particular case, the reaction due to the soldering temperature plus the moisture was so severe, it literally squashed nearly all of the spheres in the center of this package. And when the package was mechanically removed, you can see that the balls have been displaced. So that's sort of a before and after situation. But again, a nice, just so you understand what's actually going on in the process. Now, we've known for quite a few years that with area array packages and now smaller and smaller packages, that we can get warpage of the component. And the component can expand and contract and warp during the soldering operation or rework operation, which may not cause a failure of the part, but it might lead to discontinuity, open solder joints. And this is why a lot of contract manufacturers spend a lot of time trying to qualify a part, understand what's actually happening. So in this example, I'm just showing you how a package theoretically could warp up or down, and that then would lift the balls off the surface of the printed circuit board, or they would push them down into contact with the printed circuit board and cause some of the faults that I've mentioned earlier. Now, not only does moisture content affect the board and components during these operations, but again, it can cause the board to flex and move and expand and contract. So sometimes you might find on ultra fine pitch assemblies on larger boards that the positional accuracy of the component and the board pads change because of moisture content. And certainly I know a few Japanese manufacturers that bake their boards to make the boards more accurate for other operations. So it's nothing to do with delamination or damage. It's to do with accuracy of the assembly process, printing and placement. So if you get this phenomena take place on a board by movement, flexure, expansion, call it what you will, this can lead to one of the soldering defects that a number of companies have to suffer sometimes, which is a head-on pillow or head-in pillow. So what you can see here, X-ray and an optical photograph taken by myself, which shows an open solder joint. So what can happen during the soldering operation is board or component warp during the soldering operation. So they're not in contact with the solder paste. The solder paste reflows, the ball perhaps settles back down as the package starts to even itself out and go back to its normal position. But if there isn't sufficient flux left within the solder paste or on the surface of the solder paste, you get a head-in pillow or head-on pillow type open circuit. So again, you can see there are 3 or 4 things there that are impacting this particular result. Now, in addition, if you are interested in using intrusive reflow, pin in paste reflow, you've also got to look at your connectors and any parts you're going to put through the reflow soldering process. Now, these types of components are not normally qualified by the supplier and given a moisture limit or moisture sensitivity limit. So it's something you need to be aware of. Now, it's not that common, but these are just a couple of, from my reservoir of process defects that I've created over the years, and I just thought it was useful to just indicate that this can happen on other parts as well. It's not just SMT parts that we need to consider. Now, during the soldering operation, if you ever see on large packages solder balls to the edge of a package, like you see here in this example after reflow soldering, Sometimes people refer them to as solder beads, like we see on chip resistors, chip capacitors, but this is more like a squeeze out defect. So if you've got solder paste reflowing underneath a package like this, we can get this phenomena where we get small balls coming out the sides. So again, this can be based on the distortion of the package during the reflow soldering operation. And this is, again, a nice example of an SMT module. And if you look on the left-hand side X-ray image, you can see the little bead of solder which is coming out the side, but there's a lot more besides actually trying to escape at the same time. So again, if solder goes into a liquid state and it's squeezed, it's got to go somewhere. So again, just another example of it. Now, at the start of this webinar, we talked about levels, moisture sensitivity levels, and you'll find a number of standards, documents, guidelines, and also IPC standards which quote levels. And I've got a graph taken from one of those standards just to illustrate this to you. So level 1 to level 6, and there are some levels in between. Now, again, that's a reference source for you. But the important thing is, what does the component manufacturer says, or what does your customer say when we're talking about moisture sensitivity levels on particular components? So you have a guideline in terms of the time the components can be on the shop floor in an open environment, i.e. that is out of the protective packaging. You, of course, have got the ability to repackage packages. You've got the ability to bake packages after they've gone outside of their limit, their time limit, if you like. You also have the ability to restore them in in dry boxes or dry cabinets, etc. You need to manage the situation. That's what it's all about. But if you've got parts which are, level 1, level 2, it is unlikely that you really have a problem. When you go below 3 and 4, then if you don't follow the rules, and remember, you're following the rules, not my gut feel, my opinion, it's you follow the rules. That's the important thing, because if you have a failure and you haven't followed the rules, the customer and or the supplier will just highlight this to you. So again, you're having to suffer the loss of parts or assemblies because you haven't controlled the situation. So this is all documented in standards, IPC, and there are other documents available which cover this. I'll come back to the documentation and levels a little bit later on, but let's imagine you've actually got a problem. What are ways of investigating it? Well, one of them is to use ultrasound scanning, acoustic microscopy, or SAM. We used to have a system at MPL that we did studies on quite a few years back. This is just an example video which shows this test being conducted on an assembly. And the way scanning acoustic microscopy works is you're introducing sound, you're collecting the sound waves, but you're doing that while the assembly or the component is submerged in water. And you need something to connect the sensor to the sample, and that's why we use water. And what it's doing is scanning across the package and building up pictures, multiple pictures, and depending on the sophistication of the device and system you're using, it can scan at different levels and then separate those levels, just like a CT scan that you might get in hospital, which gives you a lot of data, a lot of information to understand. And then you would get a pretty picture like this. And what you can do is you can find the level where you've got potential separation or voids or cracking, and just look at that level. Whereas on these are picture superimposed on picture. So it depends on the sophistication of the tool that you're actually using. But it can show up and demonstrate to you whether the component has been damaged or not. And the easiest way is comparing it with a brand new part compared with one that you're investigating on a board. Normally you wouldn't take it off the board, ideally, because if you add the board and have another soldering operation, you may have damaged the part that you're trying to investigate by removing it from the board. So that's why you might see it done on an assembly as opposed to on an individual part. So that's on the component side, what it looks like, how it fails, what potentially can cause it to fail. Let's now look at the printed circuit board. And these two examples are just examples that I produced to demonstrate when I do rework and repair training courses. And what you can see in this example is the board delaminating. So you can actually see, and I'll just run that clip again, it's quite short, you can actually see a bubble forming. So part of the board is lifting up during the soldering operation, and there would be a gap formed inside the board because of that, and that's down to moisture. The second video clip is showing you pretty much the same thing. So reflow soldering is taking place, and you can actually see the delamination take place during the soldering operation. So that's all about moisture, and it's moisture going into the board and expanding, turning to water vapor, and then forcing the printed circuit board apart during the soldering operation. And it comes down, it's caused by a number of things. Obviously, you have to have moisture, you have to have heat, but it comes down to the quality of the board, the laminate, how it was produced, whether you've baked it, whether you haven't baked it. So there's a number of variables you need to think about. But remember, please, never bake a board unless you know the reason why you're doing it in the first place. And I'll explain about that a little bit later on. So in terms of construction of a printed circuit board, a board is 2 layers, 4 layers, 8 layers, 26 layers, however many layers of circuitry. And between that circuitry, there is an insulator. And in this particular case, we've got a material which is partly glass, woven glass, layers of woven glass, and an epoxy resin. So basically, the epoxy is sticking everything together, and the glass is then to give it mechanical stability as well as giving it the insulation qualities mixed when it has the epoxy between it. And what you're looking at here in this photograph is a board assembly, and then to the left-hand side, you can see layers of cloth, and these are glass cloth. This particular board was stripped, so the epoxy was removed with sulfuric acid. I do not recommend you do this at home, but a good friend of mine, Dennis, stripped this board half and half. So you've got half an assembly and half just glass, just as a demonstrator when we were doing a workshop together a few years back. But it's just a nice, so you get a feel for the construction. So if we go inside the printed circuit board, what we're looking at here is the glass strands across the surface, and also the epoxy resin. But in this particular example, there's a limited amount of resin. So when I've done an examination on the shop floor, I've been able to demonstrate to the customer and the supplier that there's a lack or limited amount of resin presence. And that's one of the reasons why we might get a board separate like this. Now, this is a very crude method of looking at delamination, but it only takes 5 or 10 minutes on the shop floor as opposed to an investigation in the lab. So you might then want to investigate further to get the root cause of failure, but this is just literally a knife and cutting away the area which is delaminated. You get the information you want quite quickly, within a few minutes. It's very inexpensive to do, and as long as you understand board and board construction, you can see what's right and what's wrong. And clearly, in this example, there's something clearly wrong. So what you're looking at is the copper. The holes, the square holes, are where the plated through hole will have gone through. And what's happened is it's delaminated, separated. But there is clearly, absolutely, it's clear to me that there is no bonding of the epoxy to that copper. You can see little areas, there's a little bit of glue there, but really there's a problem there. So that board was always prone to issues. It's not just me, the assembly engineer, making a mess of the soldering operation. Clearly there was a problem to start off with. So again, it's understanding the board technology, and you should be able to overcome that. So let's just talk about the boards again. There is an IPC standard dedicated to printed circuit board handling and storage, which also talks about baking. And if you look in that standard, there are recommendations to bake times and bake temperatures. Now, if you've got moisture in a board, you will always have to bake above 100 degrees C. You don't want to have too high a temperature, and you don't want to have too long a time at baking, because every time you heat up and cool down a board or a component, it has a very small effect on the wettability and solderability of that part. So at some point, you get to a situation that you are causing yourself a solderability problem, and it's more of a problem with certain finishes than others, and that's true also of components. Now, most components today are tin finish, or they are solder balls, solder spheres, which are either high temperature or low temperature balls, but it will have some effect. And I'll show you a couple of little tricks that you can use to evaluate this. So the point I'm trying to make here is that, yes, you can bake out, you can bring the board back so there's limited amount of moisture in it. It will have an effect on solderability. Certain finishes are more prone to solderability issues than others, but you just got to understand what you're doing and why you're doing it. So again, the moisture bake out is related to the laminate material type. It's also related to PCB thickness, the storage conditions, and packaging. So the original packaging you received the boards in, if they've taken 1 day or 3 months to get to you by boat from around the world, then obviously there is an impact there. Depending on the packaging will depend on how much moisture may or may not be present within inside the package. Also, the copper plating, the thickness of that copper plating, and the thickness of the copper, i.e. the original copper weight on the board, will have an effect. And also the holes, the number of holes in a board, the size of the holes, whether they're plated or non-plated. Each one of these has a small impact on how moisture escapes from a board during a baking operation. So it is incorrect for specifications to say bake for a certain time for a certain amount of hours, because every board is different. However, it's easier, and that's why people do it. But remember what I said a few slides back, never bake a board unless you know why you're doing it. And the reason being that sometimes people have a problem once, possibly with a supplier or a particular board, and they bake and it overcomes the problem, but they do it forever. Rather than finding out, has the board got better? Have you improved the quality of the board or improved the design or something other aspect? And you don't need to bake anymore. But it becomes folklore. So everybody bakes boards. And it may or may not be necessary. So that's all I'm saying. Please think about whether you need to do it or not, but certainly why you're doing it in the first place. If it's not, it's something passed down. You know, if you're a brand new engineer hitting the shop floor, you might get told, oh, we always bake that board. But why? Ask the question. So in terms of packaging, guidance, and solderability and wettability, all of this stuff is covered again within IPC and JEDEC standards. So you can review these in detail, and it gives you guidance on temperatures, time, storage conditions, etc., which we just don't have time to go into on a webinar today, but that's available. In addition, I mentioned about the IPC 1601, which is printed circuit board handling and storage. And again, there's a simulation test or simulation tests for components that go through the reflow soldering operation. Again, that might be useful for you in the future. Now, one of the other things, as well as the copy of the slides that I'm including with this particular session, is a copy of my MSD wall charts. So it's a copy of wall charts. There's I think 10 in the set, and you can use them on site for your own use. So you can print them, use them as training posters, but only for on-site use, because these are commercially sold by SMTA and myself. But it's included as an extra with this particular webinar. So let's just move on a little bit. And we're not going to go through all of this chart, but I just wanted to have it there, and it's in the slides when you receive them. And this is the sort of detail that you'll find within the standards, which give you, again, guidance on bake times, how long, what temperature for different packages and different thicknesses. So again, it's a useful source for deciding on what you're going to do with components that are susceptible to damage during soldering and rework and repair. And these times that we quote are related to the exposure time. So if you've got a board with components which have got, let's say, a 10-hour, let's say 10 hours open time. So you've opened the parts, you've placed them on the board, you've reflow soldered them, and then you're going to go on to a second side reflow, but you're delayed for a week, then clearly those components are outside of their process cycle. You have to decide what you're going to do. And this is one area which quite often is not that well defined within companies. It's not just the time the components are exposed before you solder them for the first time. You've also got to think about the second time you might be attempting to solder that board. And also when we talk about rework and repair. So baking boards prior to rework and repair is not uncommon within the industry, because you've got the components which may be sensitive, and you've got the adjacent components which may well be sensitive. So again, you've got to think about that. There's no point in repairing a board if you damage another half of it during the rework cycle. So understand the components. Some are very sensitive, some are less sensitive than others, but it's understanding that whole phenomena. Now, if you're shipping products and you're taking a product, you're sending it to somebody, he's going to do some rework for you, or you're tracking boards around the world, or you're tracking components around the world because you want to find out what actually happens to your components and your boards, then again, these types of monitoring device are quite useful. This is an example of one that I've used for monitoring temperature and humidity inside a package. And basically it's a USB, you plug it in, you program it, you give it to somebody, it's sent to the other side of the world and then comes back again, and you download the data. So again, then you can understand what's actually happening to products. I'm not suggesting you're going to do this on every single batch of products you use or do, but again, if you're investigating a problem, it's a useful way of finding out what's happened to the product, or what the packaging was like to give protection for those assemblies as they traveled around the world, like printed circuit boards, for instance. Knowing what actually happens if you're using plastic package or you're using sealed bags for boards as they come from Asia to the US over a 3-month period. What's actually happening before they hit the shops. Okay, so again, a useful tool. Baking components. Now, if you're going to bake components or bake printed circuit boards, let's talk about components first of all. There is restrictions, because you can't bake components that are tape and reeled. If you've got components, large components that are tape and reeled, and you bake them, you will affect the peel characteristic of the cover tape on the package, and you may well damage them. So again, that's something you need to consider. But if you're using waffle trays, please check the waffle trays, because just like with counterfeit components, we've also had counterfeit waffle trays, which is kind of surprising to me. But again, it's all about profit in some areas of the world. So again, just make sure they are compatible with the baking process that you're going to use. And again, most suppliers would use the same supplier of waffle trays, pretty much all the time. So check the material, check obviously the materials that you use for packaging are not going to affect the wettability or solderability of parts if you're going to be baking. And also one of the other things I always say, if you're going to bake a part or bake a board, then you use a dedicated oven. You don't use something you're using for glue curing as well, because potentially the gaseous residues that are driven off during the curing of adhesive and epoxy compounds again may cause you solderability and wettability issues on boards or components. So you're using it as a dedicated oven. You're not using it for anything else, like curing conformal coating, for instance, or baking boards that have got conformal coating on. Just think about what actually, if you put your nose inside an oven and it smells bad, you kind of get a feeling that something is being given off by the boards during the baking operation or the components or whatever else you're putting in there, and that might affect the long-term longevity of the solderability or wettability of the part. Okay, so I mentioned about components. You've got to think about compatibility. As I said, most of the packaging will not stand up to the baking temperature. Again, if you find they will, then that's fine, but it's something you need to verify. Don't just do it, you need to verify it. Now, another little trick that can be used if you're evaluating components, moisture content, soldering, etc., and seeing if the parts change dimensions, you can in fact measure them. This is not the most accurate way of doing it, but it can happen if a component is particularly sensitive to moisture and soldering, and you see a change in the package. Any change that is measurable potentially can cause damage to the parts interconnection inside the package. So again, whatever tool you might have is better than nothing at all, but it's not the ideal, but it's something that can be done to measure changes in thickness. Now, I mentioned a couple of times about baking because of moisture and its effect on our rest of our manufacturing process. And I've got a nice little test that you can use to check out components for solderability. I get this question often asked about, if I'm going to bake components and I want to bake it for X time, X temperature, what effect is it going to give me a solderability issue? Well, do a trial yourself. Do a simple trial yourself. Now, what I show you here is a slide taken out of one of our MPL presentations from a few years back with Dr. Chris Hunt. And it looks like showing measurements of components after natural aging and also after forced aging. And we can see that the graph is going down from left to right, and this indicates to us the impact on results as opposed to the results from the baking process. And this is measurements, direct measurements. However, not everybody has a wetting balance and is able to measure solderability wetting forces. So I use a really cheap test which works. And this is a solderability test I've used for many, many years because it can do everything. It can do area array, it can do all types of components. Basically, you take a glass slide, you print paste onto the glass slide, you place the component onto the solder paste, and you reflow it through your reflow oven. Same stencil thickness, same paste, same part, same profile you normally use for these types of parts, and that will give you an indication of how well it's soldered. So is it any different? Has it suffered from the baking process at all? If the answer is no, then fine. That vindicates you baking the components for 10 hours, 5 hours, at whatever temperature you've decided on, to give you confidence in those components. So that's a simple thing. So yes, you're going to use up 2 or 3 components or maybe 5 components, but if they solder, I guarantee they'll probably solder again if you add them to the board on the assembly. So you may not be wasting the parts anyway, but it's just such a simple, cheap, quick shop floor test for analyzing wettability and solderability, and it will show up marginal results. As you see on the bottom right hand corner, you can see the solder paste has reflowed, it's wet part of the leg, hasn't wetted it evenly all the way around, but it's probable that if you were to run that through your process, those parts would still solder well. But it's an indication that the baking has had an impact on the wettability and solderability of that particular part. Now, just to show you a couple of video clips, what you're looking at here is an SO package. The solder paste is reflowing, and you can see how it's wetting the side of the pin and it's actually wetting up the back of the pin. So again, in that example, I would say that that would run on a normal assembly process and give you no problems at all. If you look at these chip components, it's quite clear that there is a little bit of wetting to the surface of the chip termination, but the component actually lifted on the solder paste during reflow when it was wetting, and we've got something that's sitting proud. And that's on both ends, by the way. You might think it's just popped up like a drawbridge or a Manhattan skyline or a crocodile, but it was lifted on both ends. And these are samples that we were using as part of an evaluation. So on the component side and on the board side. So back to the boards, bake, yes. It reduces moisture present in the printed circuit board. It reduces solderability, so you've got to be careful. Time and cost is associated with baking. So that's one of the reasons why I say that if you've got a moisture sensitive part, you've got to weigh out the time, temperature, and the impact of your baking process. But you don't want to bake unnecessarily. So if your product A had a problem some years back, you really want to find out if the problem's gone away and whether you're baking and wasting time and energy for no value because the problem isn't there anymore. If you compare tin lead assembly, if you compare lead-free assembly, it's obvious that lead-free is higher temperature, so more prevalent would be delamination and distortion of packages. But if you were looking at low temperature soldering, as a lot of companies, myself included, have been looking at over the last couple of years, that's going to be another benefit for our process in terms of moisture content in packages, warpage of packages, and damage. So again, that's a benefit to us. Remember what I've said? I'm just emphasizing it again, never bake unless you know why you're doing it in the first place. So let's just pick up a couple of sort of common reasons why people bake other than cracking of parts, which is all to do with our subject of today, which is moisture sensitivity. Blowholes and pinholes. Now, I've been talking about this since my 20s, but it's still a problem we see today. Each one of these examples are in a lead-free process, but they could be in a tin lead process. So when you're wave soldering or selective soldering, if you've got a poor quality board, which is liable to outgas, then you can get voids forming. You can also get outgassing from vias in pads. So if you've got packages which have got vias, holes in the pads that you're soldering to, that gassing can come out and escape through the wall of the plating on that via. And one of the ways I test this is to use oil. And I've been doing this again since my sort of late 20s, I guess. And what I show you here, first of all, is an example of a board with vias on a LGA QFN type package. And these vias have actually been filled with an epoxy resin. And what we've got is oil sitting on the surface, and we're heating the board up to simulate the soldering operation. So in this particular situation, what I'm demonstrating to you is what would be happening underneath one of these packages with solder paste, and we'd all be blaming the solder paste or the profile for the voids within the assembly, but it's got nothing to do with that. It's outgassing from the printed circuit boards. You need to understand where the problem actually is, i.e. the root cause. Again, this is, and I apologize if you've seen this before, but as I said, I've been showing this test since I was 20. And what you're looking at here is a printed circuit board that we can test very, very simply, very cost effectively for any moisture and outgassing. So I've put some oil into the hole. I then placed a soldering iron onto the surface of the pad, so I'm heating up the assembly. The oil is staying there, and what that allows us to see is the water vapor, i.e. the bubbles, coming out through the plating, through the oil. That's what we're trying to do. And because we're doing this in this way, we could reuse the board if we make and take great care when we're doing the heating operation with the soldering iron, because you can just clean the oil off. But it's a great way of looking down the plated through hole, as you see here, this sky view, and you can see the little bubbles. And if then we go and look at it on video, this is one of the first videos I made showing this test, as I said, back in my 20s, and you can see it nicely portrays or illustrates to you gassing from the board. So this is in real time. So what you're seeing here is the outgassing from the board through the plating at different levels. And this second example on the right-hand side is far worse, the greater volume, either of poor plating, porous, or voids within the plating. So I just wanted to show you two examples. I have stacks of these in color as well, but the black and white just shows up much easier. That's why I tend to always use those. So again, a simple way of testing boards. Now back to, again, the boards and delamination. You know, I mentioned earlier about the shop floor test. I just included these 4 photographs, and the 2 from 2 different boards. And what you're looking at here, again, is poor bonding. So originally, where I've cut it out with a knife was a blister. So it delaminated. You could see it as delaminated. So basically, all I've gone round the blister and cut it out and removed that section of the board. And as soon as I do that, I've got an indication of whether there is poor adhesion originally between the epoxy and the copper. And I believe that any board manufacturer would not argue after seeing this. So the idea here is just to demonstrate, you know, the root cause. Now the root cause is moisture in the board, yeah, but the moisture in the board has turned to water vapor, which has shown up the defect in the board. Okay, so yes, it will be the moisture still in the board, but the board was suspect as well. So again, nice examples of poor wedding of the epoxy to the substrate. Okay, so packaging. Now, the majority of boards we get today, we use today, comes in some form of shrink wrap packaging. And it comes down to what you specify. If you don't specify anything different, this is the type of packaging you get. I'm not saying this is bad, I'm just saying this is the type of packaging you get. And normally speaking, you get shrink wrap over 20, 30 boards, whatever you've specified. And the key thing is to make sure that the boards are protected, the edges are protected, as well as the actual product during transport. And normally you would find inside the plastic also a desiccant and a moisture indication label. So remember that the idea of these moisture labels is to indicate the internal temperature of the product, no, the internal moisture content of the product within the plastic. Okay, so that's what they're there for. So if you were to get boards like this, where you've got the boards which are shrink wrapped in plastic, the desiccant and or the indicator strip is completely separated from the boards but sealed within the plastic with the plastic around it. What value is that? Absolutely nothing. So again, think about what's actually happening. Is it a value? Isn't it a value to you? Because it's not actually been used correctly. I'm not saying I see this too often, but I'm just making the point. So one of the other things about this type of packaging, yes, it will prolong the solderability, but it will still allow moisture to come through, and it will still allow the change in wettability or solderability of components, so of boards. So you need to still make sure that you keep them packaged as long as you can, and you'll get a certain life expectancy out of them. Now, if you pay more money, and it's all about the money, you can use bags which were designed to eliminate moisture getting inside. And these bags have been, these similar materials have been used for many years for components, and we all realize that. So they are far superior. So if you've got boards, every board is worth, I don't know, £100. I'm going to spend £1 having a better bag, or £2 having a better bag. That's the bottom line. So you've got to think about what you're trying to do, and if you can protect the boards and or components in a better way, then think about the cost, whether it's necessary, whether it's a benefit. Now, I've mentioned about components. Life expectancy of a component in a normal environment should be easily 1 to 2 years in terms of wettability and solderability. You should expect a guaranteed 1 year from a supplier. If we talk about board finishes, we have multiple different types of board finish. And if we are using gold or tin lead boards, and the tin lead or lead-free solder level boards, then it's all about the thickness of that solder coating on the boards. So if you have 2 microns, you might get less than a year. If you've got 10, 15 microns, you might get more than 2 years. If you're using nickel gold, you should absolutely expect a year's shelf life without any real problem whatsoever, and possibly longer. But when you're looking at tin finish, OSB, then again the solderability life is less, and also the impact of baking those boards again is less. So again, it's understanding those differences. Now, moving on to mentioning a report that was done at MPL. This was done by a gentleman, Owen, and another gentleman there, and they looked at baking of boards, different layers, different thicknesses, a number of holes, plated and unplated, and where parts were positioned. So basically what they did is came up with a design which allowed them to assess the baking performance of boards. And they did some simulations, and this is all covered in a report that you can get copies of from MPL. If you do a search for the MPL website, which I'll give you a little bit later on, you can find out more information on this particular exercise. And this is the modeling unit that they used to get these calculations. And you can see here the area A has got nothing in it, B is solid copper, C, you've got tracks and pads and 25% of the area is open, and you've got 1 millimeter tracks and sort of 56% of the area is open. So you've got a standard board broken up into different areas, and that allowed them to model what the baking regimes were like for different types of boards. Now, this is obviously a modeling exercise based on weight gain, weight loss, obviously, but also based on the design of the printed circuit board. There's not an easy way to come out of this and say, okay, you've got to do bake for this time, for this temperature, for this type of board, but that's something you could do yourselves to set up an appropriate bake temperature regime. So let's just pick up on some practical things now on components. And components, when you receive them in manufacture, you get them from the shop floor, from your component distribution hub within your factory, or from your supplier. So all components that are packaged within waffle trays, should always have a top tray, and that always have a top tray, and it should be bonded so they can't separate. So the components can't move around within the waffle tray. So the first example is not very good. The second example is better because it's got a top tray, and ideally within the packaging you will have an indicator strip, and also you will have a desiccant, and that package will be bonded to make sure it can't move around within the package. And you can, depending on the X-ray system you've got, you can actually, because obviously materials have different densities when you're X-raying, you can actually put a bag like this, seal bag like this, into an X-ray and look at the parts, so you don't have to open them up. And this is one of the things I use when I'm doing counterfeit workshops, just to demonstrate what you can find, what you can see, what you can detect without opening up packages, because nobody ideally wants to open up the package because of the open time of those particular parts. So just as an example, if you were to open up parts and want to reseal them, then again you would mount the parts in the waffle trays. So if you're resplitting them, you would again bond them, and the lady is not using thick rubber bands here. She's using bands which are stringed together. She's adding the two desiccator, and she's adding the indicator strip, and then she's pulling the air out. Now, with some systems, when you're resealing, you pull the air out, or you inject nitrogen in and then suck out air stroke nitrogen out to give a longer longevity of components. And then finally you're sealing it to get out any extraneous air, gas present in there, and then putting on a label. That's a sort of simple procedure. This is all covered in the IPC standards on repackaging, but again, it depends on what you want to do with your own facility. Again, similar example here. This is an example of somebody packaging a board, but again, it could easily be a series of components, bare boards. So basically, we're pulling a vacuum and then sealing the bag when the vacuum's been pulled. As you can see, it pulled down. Again, these are fairly inexpensive, these tools today, but useful. An alternative to protecting boards and components, which is kind of more popular today because it reduces the amount of handling that is sometimes necessary in manufacture. So again, we'll have lockers, ovens, humidity ovens to protect the components and the conditions they're stored in. So again, there's lots out there. And again, you follow the procedures. And again, on some systems, you've got automatic monitoring of how many times the door is open, what the moisture level is like, etc. So again, all these tools are out there, but basically to protect the boards and components from what we possibly in manufacture do to them. So let's look at just sort of talking about double-sided. I mentioned, or I alluded to, with double-sided soldering, you've got to think about second side. Now, some companies do, some companies don't. But please remember that a component absorbs moisture. So if you are running your process and you're running the boards through side one, and then within the next few hours doing side two, it shouldn't really be an issue. But remember that the reflow soldering operation, because of the time and temperature, the small time we're talking about, that's not really going to take out much moisture if it's present, but it shouldn't be present in there to start off with. But if you hold the components for a long period of time, or possibly if you're doing some other operation to the boards and components, then you might have to consider moisture. So if you're running polyimide boards and you go through a water wash and then hold the boards for a period of time before you go into the next process, again, that might be a reason for baking the board. So just think about the other parts of the process, the sort of next steps in the process, and control those just as well as you did the first parts of the process. Okay, just wanted to mention the defect database. A couple of people have asked me about this in the last sort of couple of years. This still exists, it's still there. So if you're interested, the MPL's defect database is something you can log into, and you can look at the different types of defects that are included on there, and root cause and that sort of side of things, or you can look at the reports that MPL has available. Over the years, the guys have produced countless reports on loads of different things, including the baking, which I mentioned, And again, most of those reports are available to download. So you just go for do a search for the MPL defect database, and you'll go straight to that, register, and then you'll be able to search. And here you just got to search. You can pick out defect categories, location, product volume, types of soldering process, etc., etc. Or you can just search through all the pretty pictures that I lovingly have put up there a few years back, and pick out one which then describes the particular defect, and then you can print it out and then give it to a friend, pass it on, email it to somebody, or show one of your colleagues in manufacture. So that was the whole point of doing the original MPL defect database. We don't update it anymore, but it still exists, so it's there as a resource, very useful for new young operators possibly, and or engineers in manufacture. So before we take questions, just a reminder, these are the final 4 webinars for this year. So they're coming up in September, October, November, and December. Look out for information on those. But we also do webinars on demand, and also webinar recordings. They're also available if that's something that is interesting to you. If you want a webinar on demand just for your engineers, your group, or something which is tailored, then again, we have a massive list. This is just a small selection of the topics that I do, but quite a large list on topics. So these are webinars on demand for your company, your time, a date to be agreed. So that's something that, hey, hopefully might be of interest to you and some of your colleagues. So we've got to the end of the webinar presentation. Just want to take some time now to look at defects. So just a reminder, if you'd like to send me a question about anything we've talked about this afternoon, I'll do my best to answer the question for you. So you just type your question directly into the control panel, and I'll pick up on those questions. So the first question I've had is, do all components suffer from potential damage from the inclusion of moisture? Well, obviously, well, I say obviously, perhaps I shouldn't say that, but you know, resistors, capacitors, no. LEDs, yes. So light emitting diodes, they can suffer. In the early days, the suppliers of LEDs were demonstrating that some of the smaller, simpler, cheaper parts would suffer, and I was never able to create it myself. I wasn't able to generate, and you know how I love making videos to show defects happening. I wasn't able to do that. So a lot of the simpler, smaller parts, no, but some of the more sophisticated LEDs and power LEDs we have today, potentially yes. And it's where sometimes you have molding, glass moldings, not glass, but plastic moldings over the LED, where that can expand and cause separation of the bond wires. And I have seen that, and I have examined that for companies. If we look at SOICs, these types of parts, today that would be very unusual. Mechanically, they're very robust. But when we look at area array packages, small flip chip devices, you know, anything that's got bulk plastic or a combination of plastic and fiberglass, yes. If you've got other parts that you're going to reflow, like chokes, like relays, which some of the automotive companies do, like connectors, yes. But those parts generally are not defined by their supplier as being reflowable, and generally there's no MSD limit put on them because of that reason. So again, you've got to do your own investigation and understand yourself. Next question. If I'm producing thick multi-layer boards, should I always bake? It always comes down to cost and return. When I was working in telecoms, we didn't bake boards. We were producing, thousands of 4-layer boards, 4-layer, maybe 6-layer occasionally, but thousands of these things. And I always wonder where they ever went, but that's another story. And we didn't. And the reason being a combination of things. We had our own board manufacturer, so if we had a problem, we could get very close and very friendly with him if we had a problem. But seriously, the point is that it's cost and return. So baking is a pain to do, first of all, because you can't bake, a massive pile of boards in an oven, because the capacity of the boards to absorb energy takes a long time to get up at temperature. So actually getting the baking process done is quite difficult and time consuming and costly. But if you're looking at a failure rate of, let's say, this is in manufacture, remember, and you lose 2 or 3 boards a week, it really is nothing. It really is nothing in terms of cost. So again, you've got to balance it. If you're producing boards which each board is worth a couple of £100 or more, a real good polyamide construction, so it's 22 layers, it's a big board, of course you're going to bake it, because you want to minimize the possibility of damage. You've got to weigh out the cost return, the baking, the cost, and also the liability of a board and product failing. So you've got to balance all that up. Next question. In terms of tape and reel, can I bake? Again, it's something really you've got to speak to the supplier about. Most of my experience with trying to bake tape and reel components is that the changes in peel strength characteristics of the cover tape changed, and it always tended to cause problems. Now, again, with the technology changing as it does on a regular basis, speak to your supplier. What temperature potentially is he comfortable with you baking at? But remember that really it needs to be over 100 degrees Celsius to actually get the moisture out. But also think about alternatives. We talk about lead-free technology, but with the advent and the improvement and the move towards low temperature solders is something that will benefit the industry in terms of warpage and damage to components and boards. So again, that's something that you're not just getting one benefit from that, you're getting multiple benefits. So if your product is able to use those I won't say newer materials, but materials which are becoming more popular now, that's something to investigate, because it does give you an advantage. Next question. How did you make some of your video? Oh, okay. This is always a question I get asked. When I'm doing videos, and I'm doing videos to simulate a soldering process, I try to make them as realistic as I possibly can. I try to use same temperatures. It will not be an oven, obviously, because you can't put a decent camera into an oven, because that wouldn't work. But you can also buy what we call video simulators, and these are basically boxes which you can simulate the soldering condition, just like your reflow oven, with air or nitrogen, and you have cameras mounted into special glass ports within the system. So again, you can make videos in those ways. And the key thing there is making sure there's no vibration, because if you've got vibration, the video is going to be rubbish, and I wouldn't want to show it. So again, there are techniques to do this. So they're commercially available. Certainly out of Japan, there's, I think, 3 suppliers of those pieces of equipment. And my good friend Richard Boyle at Henkel in the UK has got one in his laboratory, and he's always said that if customers wanted to do some trials, they could always do that there. So just a reminder, that's all the questions at the moment. If you've got any questions, just type them directly into the control panel, and I'll do my best to answer the questions for you. So just looking to see if there are any more questions come in. Okay, so let me. Right, the question is, should plastic through-hole parts be assessed for MSL? If you're just going to be doing wave soldering or selective soldering, I would generally say no. Where you are going to be doing pin-in-hole intrusive reflow, where you're going to be reflowing So you're looking at 220, 230, 240, maybe even 250 degrees Celsius going through a reflow process, then yes, you need to speak to the supplier, need to do some trials yourself to make sure they're compatible. Now, I worked for a connector manufacturer probably about 20 years ago, and we did a lot of work on this just to demonstrate their parts would not be affected. And this is with no baking whatsoever. So it's all about the plastic material, but sometimes it's about the molding material. Because if you've got a large cross-sectional area of plastic, as opposed to a thin area, you tend to see more cracking in some of the thinner areas where the molding material has built up stress during its flow in the mold. But again, if the material is compatible with these higher temperatures, 260 temperature, then you shouldn't really have a problem. Originally, a lot of components which were high temperature, which were designed for wave, but the actual connector body came into contact with the solder wave when we were doing tin lead technology at 250, 260 degrees C. You could see the differences in some suppliers' parts. You could always see small little cracks with the part that made contact. Even if you wrapped it in Kapton tape, which a lot of people would do in those days, you could see these little cracks. But some suppliers, different type of plastic, no problem at all. So I would say, yes, you've got to ask the question. Yes, you've got to do the tests. And only you will know the end result. But I have had problems with some customers in the past, and it does happen. So that's why I highlight it. Any more questions, please type them directly into the control panel. And again, I'll do my best to answer them for you. I'm going to remain quiet for a few moments and let you have a couple of moments just to think of any more questions, and I'll do my best to answer them for you. Okay, well, that looks like we're done for questions for the day. That's 8 questions. That was pretty good. Thank you very much for those. Just a reminder that shortly after the end of the webinar, you'll receive a copy of an email from me. If you don't receive it in the next couple of hours, check your junk file, please. And in it, you will receive a copy of the slides I've presented, plus a copy of the charts, the MSL training charts. But these are for printing and use within your own company, please. But hopefully they may be useful for you for training for the future. So once again, thank you very much for attending this webinar this afternoon. It's been a pleasure. Hopefully you'll join me on another webinar, monthly webinar, or arrange a webinar specifically for your team of staff, engineers, and operators in the not too distant future. Thank you very much, and good afternoon to you all. Good afternoon.